The first of those rules that we're going to start to use is the power rule, just in reverse. So the power rule for derivatives said multiply by the exponent and then drop the exponent by 1. Well, what we'll do now is we will increase the exponent by 1 and then divide by the new exponent. So we're just going to do the exact same thing, but in reverse. So here we have just an integral of 5 dx. So noting that the dx tells us that the variable we're using is x, and it's x to what power is currently in here?
The first?
There isn't.
Should be x to the 0 power currently, shouldn't it?
Oh, does that dx, is it just, what does the dx represent?
The dx, remember, is just the width of the rectangles. It's essentially, it's basically just a variable that's telling us, one, that we have a bunch of little rectangles inside of this curve that we are summing together, and the width of them is all dx. And it's also telling us that the variable that we're working in is x. But other than that, the dx doesn't tell us anything. So really what we've got here is an integral of 5x to the 0 power dx. And if we're doing x to the 0 power, our rule now is to go up by 1. That should bring us up to 5x to the first power. And we then need to divide by 1. So that's our new rule. To integrate any regular old function that could be written as a power, increase the power by 1, and then divide by the new power. Now, anytime we integrate something to get a function, so anytime we do an indefinite integral, so when we're not evaluating, when there's no upper limit and there's no lower limit, we always have to attach to the end of it plus a constant, because any function that looks like 5x plus any constant, when you take its derivative, will give you 5 back out. And that's how you can check and make sure you've done the integral correctly. Right? If the derivative of 5x is 5, then you're good. Okay? If this was 5x plus 7, its derivative is 5. If this was 5x plus 1,000, its derivative is 5. If it's 5x minus 1,000,000, its derivative is 5. So you know you've done it right. And we add this plus c anytime we have an indefinite integral, which is an integral that does not have an upper or a lower limit. So what we've done is we found a function that if we wanted to evaluate it on a certain range, would tell us the area underneath the function y equals 5. Everybody good with that?
Does that not mess with the area under the curve? Like if you had 5x plus 1 versus 5x plus 1,000, isn't there like a lot more area under the curve on the 5x plus 1,000?
No. And the reason is because remember what we're doing is we're evaluating. I mean, yes, there's more area underneath 5x plus 1,000 than there is under 5x plus 1. But we're not looking for the area under 5x plus 1,000 or 5x plus a 1. We're looking for the area under 5. And whether it's 5x plus 1,000 or it's 5x plus 1, let's say, if we're evaluating each of these, remember using our definite integral from, let's say, 0 to 1, that'd be pretty easy, right? Well, that becomes 5 plus 1,000 minus 0 plus 1,000, and the thousands go away. This becomes 5 plus 1 minus 0 plus 1 if we're doing a definite integral. Does that make sense? Yeah. Those constants, they fall out. They're insignificant when looking for the area underneath 5, because the definite integral gives us the ability to cancel out those constants. Does that make sense?
Yeah.
Okay, cool. All right. So what about the next one? This is 2x to the 3rd power. So the integral of that ought to be 2x to the 4th power divided by 4 plus a constant. Or we could rewrite this as x to the 4th over 2 plus a constant. So just go up 1 power and divide by the new power. Good or no?
Good.
All right. What about this one? This one we could rewrite as an integral of x to the negative 5 dx, right? That's what that is. And then how would we integrate that? It's still just a power, right? So negative 5 goes up to become negative
4.
4, and we divide by negative 4 plus a constant. Or we could say negative 1 over 4x to the 4th if we wanted to. Either one of those would be fine. Good or no?
Yeah.
Good.
All right, and what about this one? This is just a power, x to the 3/4. So if I integrate that, what's 3/4 plus 1? That's x to the 7/4, and we'll divide by 7/4. Don't forget your plus a constant, and really we normally would write this as 4/7 x to the 7/4 plus our constant. All right, everybody see how the power rule there works? Feel okay about that?
Yeah.
Yeah, cool. All right, let's do some more of them using various rules on there. So let's see if we can figure out how to integrate tangent x over secant x. Any thoughts on that one? Is that a rule that's just sitting there on your sheet to write down and do? No, there's no rule for the integral of tangent x secant x, is there?
No.
So oftentimes when you have trig functions, you're going to need to do a little bit of work to rewrite them. So tangent x is sine x over cosine x, and secant x is 1 over cosine x. And now what can we do with that? Should turn into just an integral of what?
Sine x.
So
Sine of x, right? The cosine x's and they're both in the denominator will cancel out. And on your sheet, you should see what's the integral of sine of x. Like I said, we're not gonna, it's what?
negative cosine.
Negative cosine x plus a constant. Don't forget the plus the constant. If you forget the plus the constant on a quiz, you're gonna lose a point for it. So don't lose a point for missing the plus a constant.
So there's no like inverse quotient rule that we have to use when there's division.
Nope.
We've just not gotten there yet. Or?
There is not anything like that with the quotient rule. It's an inverse of the quotient rule. No.
Okay, cool.
There's sort of an inverse of the product rule, but the inverse of the product rule is not something we talk about in this class. That's in second semester calc, so that's a BC thing, or calc 2 if you're going on to college next year. There's also an inverse of the chain rule, which we will talk about, which I was hoping we get to today, but the quiz took longer than I thought, so looks like that'll be tomorrow. But no, there's not direct inverse of that. We're not going to be able to take the integrals of as many functions as we could take derivatives of. We could take derivatives of almost any function that I gave you, right? But as far as integrals were, there's going to be a lot of functions that we can't take integrals of. I'm not going to give you any of those to worry about, but I'll discuss them sort of as we go through different types that you might not be able to do. So what about this next one? 5x cubed. What should 5x cubed become?
5x to the 4th divided by 4.
5x to the 4th divided by 4. And what should cosine x become?
Sine x.
Just sine x, right? We know the derivative of sine is cosine, so the integral of cosine should be sine. And don't forget plus the constant. And that's on your sheet. So everything on that sheet you should memorize in the next day or two. Okay. What about this one? At the bottom there, that first term should become what?
Eight t to the 4th over 4.
8 to the 4th over 4, or, well, we'll write it that way. We'll write this in 2 steps. 8 to the 4th over 4. And then this one is minus 6 t to the 1/2, so that should become minus 6 t to the 3/2 divided by 3/2. And this last one should become plus, that's t to the -3, so that should become t to the -2 divided by -2 plus a constant. And I'd really like you to simplify this down to 2t to the 4th. And then this one, if you divide by 3/2, that's like multiplying by 2/3. So that would be minus 4 t to the 3/2 and then minus 1 over 2t squared plus your constant. Good or no?
Good.
Good.
Excellent. All right, let's keep doing these then. Let's look at this one. X squared minus 1 squared over x squared. So I think it was Alex, you were saying something about like an inverse of the quotient rule, right? That looks like that'd be perfect here. But since we don't have one of those, we're going to have to find another way to deal with this. And one of the ways to deal with rational functions is, especially when there's, well, definitely when there's only one single term in the denominator, expand out your numerator as much as you can. Right, x to the 4th minus 2x squared plus 1 over x squared dx. And then you should be able to rewrite this. If I have a fraction with a single denominator, I can just take each piece of it, right? And divide each piece of it by that denominator and get a new function. So this should be an integral of x to the 4th over x squared is x squared. Negative 2x squared over x squared is -2, and 1 over x squared is x to the -2 dx. And now it's in a nice simple form for us to be able to integrate using the power rule. So what should that become?
X cubed over 3.
Cubed over 3 minus 2x.
2x.
And then x to the -2, I go up to -1, and then we divide by -1. So that'll be minus x to the -1 or minus 1 over x plus your constant. Don't forget plus a constant every time. Everybody good with that?
Yep.
Awesome. All right, what about this next one? What are we gonna do with that?
Simplify.
Simplify. Okay, how are we gonna simplify?
Break up cotangent.
Break up the cotangent, is that what you said?
Make it in terms of sine and cosine.
Make it in terms of sine and cosine. Okay, we could try to do that. So what's that going to give me? That's going to give me an integral of 1 over cosine. And then cotangent in the denominator is like having a tangent in the numerator. So that'd be times sine over cosine.
Didn't you make it in terms of secant and tangent?
Yeah, that'll be even better. So let's do that. This becomes a secant and a tangent, right? And what's the integral of secant tangent? Well, it should just be from your sheet that I just sent to you. The integral of secant u tangent u du is
Secant u plus c.
plus a constant. All right. So recognize that the derivative of secant is secant tangent, and if you could get this to look like secant tangent, then you're in good shape. Everybody good there?
Yeah.
All right, we're gonna just keep working through some more of these. Why don't you guys try and do these 4 on your own real quick? So I'll give you guys, I don't know, 2 or 3 minutes to try and work through these 4 on your own, then we'll talk about them. There you go. So the first one, negative x to the -2, that goes up to a power of -1, and you divide by -1, which cancels out the negative signs. So you just got x to the -1 plus a constant, or 1 over x plus a constant. So that's a good one to remember, right? That the negative x to the -2 shows up fairly often to become 1 over x, or x to the -2 to become -1 over x. What about the next one? 3x to the fourth should become 3/5 x to the fifth. And then negative 2x to the negative 3, that goes up to be x to the negative 2. And then when you divide by the negative 2, you get plus just x to the negative 2. And then what about the antiderivative of secant squared? That's just a formula from your sheet. What should that one be?
Tangent.
Tangent x, right? And the derivative of tangent is secant squared, so that makes sense. What about du over u squared plus 1?
Inverse tangent.
Yep, that's just the inverse tangent. So recognize those inverse trig functions. Don't forget the plus c. What about e to the x? The integral of e to the x is just e to the x, right? Since the derivative of e to the x is e to the x, the integral of e to the x is e to the x. So 2e to the x ought to just be 2e to the x. And then the secant tangent, we've had that one already. That's just secant. And then the square root of x, that's x to the 1/2, right? So that ought to go up to x to the 3/2. And when you divide by 3/2, that's like multiplying by 2/3. And plus your constant. Everybody good with those ones? Any issues there? Any questions on those?
So on the last one,
Mhm.
so 2e to the x just becomes 2e to the x again. How does that work?
Well, what's the integral of e to the x, right? The integral of e to the x is just e to the x plus your constant, right? The derivative of e to the x is e to the x. So the integral of e to the x is e to the x. A constant, remember, is just its own thing. So just keep it there or pull it outside. You know, you could always separate this into 3 different integrals and pull the 2 outside if you wanted to, if it confuses you, but that's not necessary. But yeah, the integral of e to the x is the same as the derivative of e to the x. It's e to the x.
Couldn't 2e to the x also be, or like the integral of that could be e to the 2x?
No, because that would, the derivative of e to the 2x is 2e to the 2x.
Oh,
You'd have to have a 2x in the exponent, which we're going to deal with. We're going to have those, not today, but we'll have some of those tomorrow, and we'll learn how to deal with those. But no, if it's just an e to the x, no matter what the constant in front is, the integral and the derivative are both the same. They're just that same function. All right. So let's take a look at evaluating one of these using a definite integral. So this is now a definite integral because it has limits. And when we do a definite integral, we don't have to worry about adding the plus c because we're actually going to evaluate our integral at certain values. So the second part of the fundamental theorem of calculus says, take the integral of x cubed plus 1. Well, what's the integral of x cubed plus 1? Ought to be x to the
fourth divided.
X to the 4th over 4 plus x.
And we'll just evaluate that. And this is how I'll notate this, from -1 to 3. And so that means do 3 to the 4th over 4 plus 3 minus -1 to the 4th over 4 plus -1. Everybody good with that? I just plugged in 3. That's what this is. And I plugged in -1, and that's what this is. Good or no?
And you're just subtracting them because that's what you do when you have the upper and lower limits.
That's
Right.
correct.
Okay.
That is correct. That is the second part of the fundamental theorem of calculus. And so 3 to the 4th power is what, 81? So we got 81/4 plus 3 minus 1/4 minus 1, which ought to be 81/4 minus a 4th is 80/4, which is 20. And then 3 minus a -1 ought to be a plus a 4. So the integral from -1 to 3 of x cubed plus 1 dx is 24. And that's, you will probably note, a whole heck of a lot easier than writing out a limit as n approaches infinity of a sum from k equals 1 to n of x sub k cubed plus 1 times delta x, and figuring out that delta x is 4 over n, and that x sub k is negative 1 plus 4k over n, and plugging it all in and trying to evaluate. This is a little bit easier, huh?
Yeah.
Yeah, it'll make you appreciate this just that much more that you had to do the other way. Cool. All right, last one. Yeah, last one. So we have an integral from -1 to 1 of r plus 1 squared dr. How are we going to deal with that?
Expand it.
Expand it out. That is the only method we've got at this moment. Now, tomorrow we're going to learn some other ways to deal with this. But if I expand this out, that becomes r squared plus 2r plus 1 dr. And now we just integrate and evaluate from -1 to 1. So what is the integral of r squared? It ought to be
R cubed over 3.
r cubed over 3 plus the integral of 2r is just r squared, and then plus the 1 is just plus r. From -1 to 1 gives us 1/3 plus 1 plus 1 when we plug 1 in, minus -1/3 plus 1 minus 1 when we plug in -1. So we've got 1/3 minus -1/3, 2/3. We got 2 minus 0, so 2/3 plus 2, or 8/3. Everybody good there?
Yeah.
Yeah.
Cool.